Good afternoon and welcome to the 2021 Virtual Discovery Talks. I'm Dan Lowenstein, Executive Vice Chancellor and Provost, and it is my honor this year to host the Discovery Talks virtually, bringing back one of the weekend's most popular events. So thank you so much for everyone for tuning in. I'm excited for you to hear from this year's lineup of speakers, so my introductory remarks are going to be brief. Now, as you know, our faculty members are engaged at the forefront of biomedical inquiry with research on topics ranging from molecules and cells to individuals and whole populations. The aim of the Discovery Talks is to give our alumni a taste of the exciting research that's taking place at UCSF right now, which allows us to attract the very best PhD students and postdocs to come here and work with our talented faculty. Now, the mentor-mentee relationship is mutually beneficial. Students and postdocs learn side by side with world-class scientists and scholars, and in turn, those scientists and scholars get the benefit of a highly skilled team to help them carry out their research. Graduate students and postdocs are the engines that drive the research enterprise, contributing to the discovery and innovation that are the hallmarks of UCSF. And now, on with the show. I'm happy to share that our speakers are here with me live and that we've taken all the necessary public health and safety precautions. And we hope that seeing them in person will emulate as much as possible the immersive experience the Discovery Talks create at an in-person alumni weekend. Each of the speakers will make their presentations one after the other with just a short introduction from me in between each talk. So, our first speaker is Dr. Stephen Floor. Stephen is an assistant professor in the UCSF School of Dentistry's Department of Cell and Tissue Biology. His research seeks to understand how cells use information in RNA molecules to make decisions. His lab studies how these decision-making processes normally work and how they go awry in cancers and developmental disorders. The title of his talk is Learning RNA's Rules.
Hi, I'm Stephen Floor, and I'm an assistant professor in the Department of Cell and Tissue Biology. I'm also an alumnus of the Biophysics graduate program in 2011. So I remember when Jurassic Park came out, and I think I was about 12. I went to see it in the theaters, and I was sitting there in the seat with a box of candy. It was probably some hot tamales. And I'm watching on the screen as Mr. DNA comes on to explain how DNA is the blueprint of life. And so they can take the DNA from the mosquito and amber, and they can fill in the gaps with frog DNA to make dinosaurs. But what Mr. DNA didn't explain is how you actually take that blueprint of life and turn it into life itself. Now, it turns out that DNA isn't actually very useful until you make it into RNA. DNA is like the master copy of some Lego instruction set that's stored at Lego HQ in some secure server. But in order for it to be useful, you have to make a copy of those instructions that then get sent out along with a bunch of Lego bricks so that somebody like my 7-year-old son can receive those and build them into an actual Lego set. In this analogy, the master Lego instructions are like DNA, the copy of the instructions that get sent out in the mail is RNA, and the individual Lego bricks are the amino acids or the building blocks of proteins themselves. Now, proteins are incredibly important for our body. Proteins are what carry oxygen around in our blood. Proteins send and receive signals in our brain. Proteins tell our cells when to divide and when to stop dividing. So it's extremely important that we make the right proteins, that we make them correctly, we make them in the right amount, we make them at the right time. My lab seeks to understand these rules inside of RNA molecules that specify when, where, and how much of a protein should we make. Now, if you get a really complicated Lego kit, like the 4-headed dragon that my son received as a present, then that Lego kit is going to have multiple books of instructions. And RNA molecules, or messenger RNAs, are the same way. They have a book of instructions that is at the beginning that talks about how much of this protein should I make and when should I make it. They have a book of instructions that's in the middle that talks about exactly how should I stitch the amino acids together to make the protein. And they have another book of instruction that sits at the end that says where in the cell should I make this protein and how long should I keep this RNA molecule around. And together, all of these instructions have to be decoded to figure out how much protein and when and where to make it from a messenger RNA. Now, because biology is basically just random changes that are fixated by selection, these rules can be baroque, confusing, and idiosyncratic. And so my lab uses top-down and bottom-up approaches to try to understand how these rules work. We take individual RNA sequences and we make changes to them so that we can understand what those changes do. And we also make whole collections of engineered RNA molecules that we can use to explore this space in an unbiased way. And together, we're seeking to understand the rules of RNA. Now, I want to take a moment on this slide to recognize the 13 people that I've had the honor of working with so far since starting my lab. Now, these people come from all over the United States and from all over the world. They have diverse perspectives on the world and life experiences. And these perspectives and combinations are critical both for innovation, because they lead to creativity and spontaneous thought, but also because trying to understand the natural world is fundamental to humanity, no matter where humans are born. And there's always going to be some people that want to dedicate their life to that. And because of this, and because of the connection to innovation, it's really imperative on us to make sure that science is as accessible as it possibly can be. And I especially want to celebrate all the people that have been in my lab over the last year for everything they've done, because this year has been so hard for so many of us. OK, back to RNA. So we know that the instructions in RNA molecules are read out by other RNA or protein molecules, and that if changes happen to these decoders so that they can no longer correctly read the instructions, tragedy can result. My lab studies a gene known as DDX3X, which is a protein that interacts with some of the most challenging RNA molecules to help figure out when, where, and how much protein should be made from them. Now, DDX3X is required for life in all animals, and even in simple organisms like yeasts. But occasionally, people are born with spontaneous mutations to DDX3X gene that are not present in either of their parents, but emerge spontaneously in the sperm or the egg. And when people are born with mutations in DDX3X or changes to the gene itself, these people suffer severe neurodevelopmental disorders, including autism-like features, speech and language delays or disorders, and movement disorders. And together with Elliot Scher in neurology at UCSF, Debbie Silver, who studies brain development at Duke, and with the support from the DDX3X Foundation, we're trying to understand both how this disorder emerges and what we might be able to do to treat it. Additionally, once we understand the rules of RNA, we can write our own RNA sequences that tell the instructions to make specific proteins when, where, and in how much. Now, if I'd given this talk a couple years ago, people might be wondering, why would I want to make my own RNA sequence? But many of us, including myself, are intimately familiar with the power of RNA to make new proteins, because many of the COVID vaccines are actually based on this RNA technology. But the COVID vaccines are just the beginning. Once we understand the rules of RNA that specify whatever protein we want to make, we could restore the expression of something like DDX3X. We could teach our body's immune system to recognize new proteins that are present only on the surface of cancer cells. Or we could perform a whole variety of other approaches. We could perform genome editing in specific cell types and at specific times. But we can only do these things once we intimately understand the rules of RNA. RNA is thought to be the origin of life, but there's so many mysteries that are left to be decoded. My lab seeks to understand the rules of RNA so that we can better understand basic human biology, human disease, and write our own RNA therapeutics. Together, we believe the future of RNA is bright, and it's our hope that in the next version of Jurassic Park, perhaps they can use Mr. DNA to teach us how RNA turns the blueprint of life into life itself. Thank you.
Thank you, Stephen. Our next speaker is Dr. Kelly Knight. Kelly is an associate professor and vice chair of the UCSF Department of Humanities and Social Sciences and an affiliated faculty member in UCSF's Institute for Global Health Sciences and Center for Vulnerable Populations. Her National Institutes of Health-funded research explores the health, social, and policy implications of homelessness in the Bay Area and the consequences of reduction in opiate prescribing in safety net primary care settings. The title of her talk is Structural Analysis is Critical to Understand and Solve the Crisis.
Thank you. I first came to UCSF in 1996 to work with HIV-positive injection drug users, and I'm a proud graduate of the doctoral program in medical anthropology here at UCSF. And today, I hope to use my opioids research to demonstrate two things. First, health crises are social crises, and social problems make health worse. And second, social scientists can play a role as thought leaders and collaborators to identify the structural factors that contribute to health crises, help us understand them and solve them better. Just as physicians can offer a biological diagnosis, mental health and treatment professionals provide a psychological or psychiatric diagnosis, medical anthropologists like myself can offer a sociostructural diagnosis. These diagnoses are not mutually exclusive. They scaffold atop one another to give us a more comprehensive understanding of the health experience and the way that that health experience relates to social policy and institutional realities. The 19th century physician Rudolf Virchow, who's considered the founding father of modern pathology, as well as a founder in social medicine, said it well in 1848. If medicine is to fulfill her great task, she must enter the social and political life. For do we not always see diseases of the populace traceable to defects in society? As medical anthropologists, we're deeply invested in understanding the complex relationship between diseases of the populace and defects in society. We ask the question, what are the conditions of possibility for health, for life? So let's start with life. In my book, Addicted, Pregnant, Poor, I followed the precarious pregnancies and documented them among women who were both opioid dependent and unstably housed in San Francisco. I followed 19 women who had 23 pregnancies over 4 years. This room that you see is a room in a daily rent hotel in the Mission District that cost $50 a night to rent. This is the room where Lexi lived when she was pregnant. It's the room where she went into labor. It's the room from which she was rushed to the hospital where she later lost her child. I followed women like Lexi down the hallways of these rooms to drug treatment appointments, welfare visits, housing appointments, and to their doctor's appointments with clinics and in the hospital. I also talked to those doctors, policymakers, welfare bureaucrats, other influencers who had decision-making power to structure the outcomes of pregnancy for the women who lived in these daily rent hotels. And let's talk a little bit about the national context. Many people are aware that we've had an opioid crisis existing in the United States for many decades now. Now, some of the structural forces that contributed to the opioid crisis are well known at this point. Pharmaceutical greed amongst opioid manufacturers and distributors and a lack of federal regulation to control that pharmaceutical malfeasance or to regulate a rampant opioid overprescription. But there's longer history related to structural racism that many people don't know that intersected in the lives of the women that I worked with, those who are opioid dependent and pregnant. First, a failed war on drugs. We've had drug war policies in the United States that have focused on penalization and criminalization of substances and people with substance use disorders for decades, which makes incarceration much more common than treatment access for most. We also have a history of welfare reform and family management systems, which the historian Dorothy Roberts documented in real time in the 1990s, that created a bifurcated system under which families and parents of color were targeted for family separation, while other families were not so targeted. This was based on faulty science and moral panic, but the implications of it were decades long lasting. We're still recovering from them now. And so let's look back on Lexi's experience. So Lexi was a Black woman who was born about 50 miles outside of San Francisco and grew up there. She grew up in the 1970s experiencing some of these early forms of these welfare and family adjudication processes in which her home would be subject to sudden visitations by welfare officials looking for people not on the lease, looking for some form of fraud. When she came to San Francisco and later came to become involved in heroin, it was after many, many decades of working, and she came to that late in her 1930s. When she became pregnant with her first son, she was an active heroin user and was very, very concerned about being able to manage her recovery and also take care of her son. She was so concerned about being separated from her son that she ended up placing him with a relative to take care of him in order not to lose him to the foster care system. So when she became pregnant with her second child, Lexi experienced a miscarriage. During that miscarriage, she was eventually released from the hospital and immediately detoxed from her methadone program. Why? Because her methadone was linked to her pregnancy status. The funding system was structured in such a way that she was not eligible for methadone if she wasn't pregnant, but being pregnant made her eligible. Having miscarried mean that she was immediately detoxed from her methadone program, experienced opioid withdrawal, returned to street heroin use and homelessness for several years. So this is a long arc of structural racism and management of Lexi as a person with a substance use disorder over time that contributed to her decision-making in that third pregnancy that I was speaking to, which took place in the room that we see behind us. So Lexi avoided prenatal care because if she went to prenatal care, she feared that she would then face the loss of her child should that child be born. If she miscarried again, she feared loss of treatment. She felt forced to choose between the management of her opioid use disorder and her prenatal care. This is a choice that no one needs to face. We have protocols and systems in place that are evidence-based to be able to manage opioid use disorder among pregnant people. We can help the pregnant person who has opioid use disorder stabilize and have a safe birth, and we can help the neonate, if that neonate is exposed to opioids, to make neonatal abstinence syndrome a treatable and transient condition for the child. This can be different than it is, but Lexi, it wasn't the science that kept her out of prenatal care. It was fear of the healthcare system and the social welfare system and the experiences of discrimination that she had been through throughout multiple pregnancies. So when she arrived at the hospital in an obstetric emergency, she was traumatized, she was terrified, and she was told by the doctors and nurses that she should probably be thankful that the child didn't survive, because likely the child would have ended up in the foster care system. So we see these levels of discrimination against Lexi because of these histories of structural racism and histories of discrimination, the way to single her out as a person with a substance use disorder and create a picture of her as an undeserving mother, as someone whose reproduction doesn't matter. So where do we move forward from here? Well, since this experience, I focused in 3 areas. 1, institutional responsibility. I focus on medical education, and I brought a framework of structural competency, the medical education program at UCSF. Now, structural competency is a framework that asks health professionals to recognize and respond to the structural factors, the policies and systems that create vulnerability for poor health, and then intervene upon them, rather than just thinking about only providing care, only moving forward with the science. We need to have a structural analysis to be able to improve care and ensure that it's successful. We took Lexi's case, and I collaborated with an OBGYN chief resident and faculty member here at UCSF, created a case study in the New England Journal of Medicine that we use in medical education for the second year medical students at UCSF during their OBGYN rotations. We talk about Lexi's case. We talk about the structural reforms that are necessary to ensure that we experience a different outcome when situations like Lexi's situation come into the hospital. Second, I collaborate with national organizations that are trying to change policy to repair the damage of a decades-old war on drugs, to focus not on criminalization, but on treatment access, and to elevate the leadership of people who have experienced substance-involved pregnancies, experienced the management of their families, and taken into account the solutions that they think will work best for them. I can be an aid as a social scientist to provide a structural analysis and help support that important work. And lastly, I work locally with service organizations in harm reduction, drug treatment, and housing to ensure that locally here in San Francisco, the programs are meeting the needs and alleviating the structural harm that so many people with opioid use disorder experience when they're pregnant. That is because health crises are social crises. And if we can address social problems through a structural analysis, we have a much greater possibility of changing the conditions of possibility under which health can happen for Lexi and others like her. Thank you.
Thank you, Kelly. Our next speaker is Dr. Cord Kober. Cord is an assistant professor in the UCSF Department of Physiological Nursing and an affiliated faculty member of the UCSF Baker Computational Health Sciences Institute. His research seeks to understand the molecular mechanisms that underlie common symptoms in cancer patients to discover targets for therapeutic intervention and identify the demographic and clinical characteristics that place cancer patients at increased risk for a higher symptom burden. The title of his talk is A Translational Approach to Improve Symptoms in Patients with Cancer.
My assumption is that all of you have personal experience with cancer or its treatment. For me, my father was diagnosed with cancer and underwent chemotherapy. The program of my research focuses on two of the most significant and unsolved symptoms associated with cancer and its treatment, namely fatigue and chemotherapy-induced neuropathy. To give you an idea of what a patient experiences when they experience fatigue, imagine the last time you were exhausted. And take that feeling of exhaustion and being worn out and amplify it by a factor of 10. Cancer-related fatigue is more severe, persistent, and debilitating than the fatigue experienced by the general population. In terms of chemotherapy-induced neuropathy, imagine the last time your feet fell asleep and that feeling of pins and needles when blood started flowing back to your feet. Now, imagine that again, a couple fold times increased, but also in your hands as well as your feet. And imagine that during treatment, and for some, into survivorship. We have no ways to prevent these symptoms, and we have no efficacious treatments. So the focus of my program of research is to understand the characteristics and the mechanisms that are associated with these symptoms, and to develop treatments. I'm proud to be part of an interdisciplinary team whereby I get to work very closely with clinician and researchers. We start our research at the bedside, where we perform clinical studies, where my clinician colleagues will characterize the patients that are participating in these studies. The characterizations include patient-reported questionnaires and outcomes, reviews of the medical record, and objective assessments by the clinicians. These characterizations produce hundreds of demographic and clinical variables, and we are able to identify and provide in-depth characterization of these patients using this information. This in-depth characterization is critical and very informative for the research that we do in other areas. In parallel to these characterizations, we are also collecting biomarkers and biotissues and biobanking this material. We primarily convert this biological material into large-scale molecular data. To give you an idea of the types of data that we collect and what can be useful for, recall the central dogma of molecular biology. Here, the DNA as inherited material transcribes into RNA, and some of that RNA can be transcribed into proteins. If we add an epigenetic component to that, whereby the environment can feed back into the loop, we can observe some ways in which the environment may impact changes in gene expression. To use a very commonly used tissue type as an example, peripheral blood, here we can extract DNA, sequence it, or genotype it. And by analyzing that associated with our symptoms, we can understand the heritable component to symptom severity. Another material that we take advantage of is the functional products of these genes, which is RNA and proteins. Now, this material is very exciting because it provides insight into the activity of these genes at the time of assessment at the molecular level. In addition to the DNA and, let's say, RNA, we also look for epigenetic signals. Please recall, epigenetics is the study of changes in gene expression that are not related to changes in the underlying DNA sequence. One type of epigenetic mechanism is DNA methylation, and with DNA methylation, this is when a methyl group gets attached to the DNA molecule, and DNA methylation can change the DNA activity. So these data types have different scales and modalities, and we use a couple of different approaches to try to integrate them together. We take advantage of existing computational tools as well as develop novel ones in our lab. And we use what's called a systems genomics approach, which is partially an integrative omics approach to better understand what's going on. Here, we take these multiple types of data, the genomics, the genetics, the epigenetics, and we analyze them together using a systems biology approach. This systems biology approach takes the characteristics of a symptom, tries to understand their interaction through computational and experimental methods. By using this approach, we can get a better understanding of how these data types or these fundamental biological processes operate. And by better understanding these fundamental biological processes, we can better understand the molecular mechanisms that are contributing to these symptoms. In parallel to this molecular characterization, we're also implementing machine learning models to develop predictive models for symptom severity. An attractive aspect of machine learning approaches is their ability to handle large-scale sets of predictor variables. In our sense, that's very useful because we have hundreds of demographic and clinical variables, and we have millions of molecular markers. So far, we have developed predictive models to predict symptom severity, and in addition to the ability to predict those patients for which are at high risk for high levels of symptoms, we can also identify the risk factors that contribute to that outcome. Finally, I'd like to share with you some exciting new directions in our research whereby we can take advantage of this well-characterized data set and molecular information that we have to develop profiles and target individual or identify targets for therapeutic intervention. And here we're collaborating with other researchers at UCSF to implement drug discovery and repurposing pipelines. Drug discovery and repurposing approaches have a number of advantages over previous or other fundamentally used drug discovery approaches. Hereby we can focus on drugs or compounds that have been previously characterized, potentially for use in patients, as well as take advantage of existing, say, drug and target interaction databases to help us get to potential compounds of interest quicker. Once we have compounds of interest that show the potential to treat or prevent these symptoms, we're working with other researchers here at UCSF to evaluate for these compounds in both in vitro and in vivo preclinical models. For those compounds that demonstrate some promise, we're going to be taking those for more in-depth characterizations and potentially move into early phase trials. It's important for me to share that this transdisciplinary work can be successful here at UCSF because of the wide variety of work that happens across campus in clinical, preclinical, computational, and basic science. UCSF is a unique and special environment where translational and interdisciplinary work such as ours can thrive. Ultimately, the work that we're doing, characterizing and understanding the contributions to these symptoms and developing therapeutics will be used back at the bedside for the patients so that we may help them with their experience of these potentially devastating symptoms. Thank you.
Thank you, Cord. Up next is Dr. Tamara Alliston. Tamara is a professor in the UCSF Department of Orthopedic Surgery and the Department of Bioengineering and Therapeutic Sciences. Her laboratory, which focuses on skeletal mechanobiology, investigates the interaction between physical and biochemical signals in the control of skeletal cell function and the role of these pathways in skeletal health and in diseases such as osteoarthritis and osteoporosis. The title of her talk is The Buried Treasure in Our Bones.
Half asleep, from the back row of a cavernous medical school lecture hall, suddenly projected on the screen in front of me were the most beautiful cells I'd ever seen. Buried deep within the calcified core of our bones, these osteocytes in this slide extend these dendrites to connect to one another and to distant blood vessels, with each dendrite traveling through its own tiny custom-made canaliculi. These cells captured my imagination. Maybe, like me, you hadn't thought much about the skeleton. We know that it's the source of what we know about dinosaurs from their fossilized remains, or the way we get our first glimpse of a baby from an ultrasound. Or maybe it's just the natural helmet for more interesting organs. But for me that day, the skeleton was something other than dry and dusty. It was dynamic and dancing with life. I was full of thousands of questions. How did these cells do that? My imagination was captured, and that was the day I became a treasure hunter. Like any treasure hunt, this one was full of twists and turns, not the least of which was the fact that I had just decided to pursue my PhD in a lab that studies the ovary. But the lure did not go away. When it was time to pursue a postdoc, I followed earlier generations of treasure hunters to Northern California, where they dug for gold and where I dug in the bone to find more about these cells. I didn't have a map, and studying bone is literally very hard. All of those tools I had used and learned as a graduate student to study the soft and squishy ovary were no match for this hard tissue. We either had to learn new ones or invent them ourselves. Our first big break came when I found another community of scientists who were just as curious and passionate about bone as me, material scientists and engineers. They used tools I had never heard of, atomic force microscopy. They went into this wonderland of Lawrence Berkeley National Labs, using the synchrotron and so many incredible resources to uncover materials and what makes them strong. So working together with my mouse models and their sophisticated molecular mutations and their incredible toolkit, we began to understand new molecular and mechanical mechanisms of bone strength. So I feel squarely like now I'm at the place where X marks the spot. And I'm delighted to be able to share with you some of what we've learned along the way about osteocytes. Osteocytes make up 90% of the cells in our body, and their dendritic network rivals that of the nervous system. If you were to lay all those dendrites end to end, they'd go around the earth 4 times. Every single time we take a step or hit a tennis ball, the forces cause a flow of fluid through those tiny canalicular channels. And each time, it stimulates the osteocyte with a new message saying, hey, build more bone right here, right now. So in this way, these cells help to orchestrate the strength of our skeleton. That alone would be enough for any treasure hunter. But it's even more remarkable because in the last few years, our lab and others have been beginning to understand how these cells also help to influence our systemic and metabolic health. They even not only control our skeletal mechanics, but might even influence the way and how much we eat. So at this point, we have so much more to learn. And when we turned then to a new image that stimulated our curiosity in the same way. This time, it came from my graduate student in bioengineering, Charlie, who was developing and pioneering his own way to chip away at the mysteries of bone. He decided to try a new experiment to visualize the canalicular network deep inside the bone, and you can see that it was an unparalleled view of these cells. It was even more amazing when Charlie then showed me the same kind of technique applied to old bone. And what you can see with aging is that this canalicular network is lost. Nearly 50% of the canaliculi are just gone. And just like before, in an instant we knew that this network was important for age-related loss of skeletal health and diseases like arthritis and osteoporosis that affect about 50% of the population and account for the second leading cause of disability, second only to mental health. We were clearly convicted we need to understand, how does osteocyte aging contribute to age-related skeletal disease? We've made some new discoveries, and now that we understand that osteocytes are the target, are beginning to forge new collaborations with people who are doing high-throughput drug screening so that we can identify compounds to rescue osteocyte aging. We're beginning to collaborate with computational genomics experts so that we can mine this treasure trove of 500,000 patient database records and genomics to uncover the new molecular drivers that control osteocyte function and health and how it goes wrong in arthritis and osteoporosis. We also believe that this line of research is going to reveal new ways that osteocytes participate in age-related skeletal disease within and beyond the skeleton. The truth of the matter is, though, that even if we were to find the cure and understand the mechanism of osteocyte action, it wouldn't help everybody. The hard reality is that musculoskeletal disease has a disproportionate impact on women and on communities of color. Compounding that problem is the reality that relative to all the other biomedical and research workforces, musculoskeletal research and orthopedics is the least of the diverse specialties, with an underrepresentation of women and Black and brown people. Here we are again, convicted, knowing there's a treasure to find. And we feel like we have no map, but indeed at UCSF we do. The new UCSF Musculoskeletal Center will collaborate with leaders who are already pioneering research in health disparities and improving the recruitment and success of all learners. So we hope that this new chapter of our treasure hunt will lead us to find ways to chip against these petrified problems and uncover new brilliant and precious solutions. At this point in our treasure hunt, we continue on motivated by what we can discover. And I'd like to leave you with one question and comment. What is your buried treasure? I think you'll know that you found it when you can feel it in your bones.
Thank you, Tamara. Our final speaker is Dr. Jason Sello. Jason is a professor in the Department of Pharmaceutical Chemistry. His current research efforts are focused on the discovery and characterization of novel drugs that induce anesthesia or prevent infections. The title of his talk is Accelerating Neuroactive Drug Discovery and Development Using Zebrafish.
Thanks, Dan, for the introduction. Neuroactive drugs are truly miraculous. Once administered, they enter the bloodstream, they traverse the blood-brain barrier, and then bind neurons and affect their activity. And the consequences of that modulation of neuronal activity can be alteration of mood, induction of sleep, or even loss of consciousness. Now, the discovery of neuroactive compounds historically has been a very challenging process. It's labor-intensive, it is very expensive, and it also requires a lot of serendipity and luck along the way. So in a typical neuroactive drug discovery program, dozens or hundreds of compounds will be screened in mouse models, for example, at many different doses, looking for therapeutic effects, or even simply looking for activity. So my research group at UCSF has been very much interested in trying to make the discovery of neuroactive compounds much more efficient, faster, simpler, and cheaper. So our strategy for doing this has been to repurpose and reimagine technologies that are used for high-throughput screening in vitro biomedical research. We want to reimagine, readapt those for in vivo studies. So our approach is illustrated here on this slide. I'm showing you a 96-well plate, which is a workhorse of high-throughput screening, high-throughput in vitro studies. And in this 96-well plate, there are actually 600 animals. In each one of the wells of this plate, there are 6 larval zebrafish that are about 7 days old. Now, zebrafish turn out to be very interesting from an experimental standpoint, a drug discovery standpoint, because they share about 70% of their genes with humans. The homology is also reflected in the fact that their organ systems are very similar to those that we find in humans and other mammals. And the organ systems are so homologous that, in fact, if you treat zebrafish with clinically used drugs, what you'll find is that the physiology of the zebrafish will be modulated. And that's what I'd like to show you here on this slide. Okay? If you look at the top part of the slide, you see these zebrafish larvae swimming around happily in the absence of a drug. As you go down the rows of this plate, you'll see that there are 7 different concentrations of an anesthetic called etomidate. And if you compare the top row to the lower rows, you'll actually see that there is a decrease in motor activity of the zebrafish globally. But I'd like for you to pay a little bit more close attention to what's in the plate. If you look at the bottom of the plate, you'll actually see a red dot corresponding to when a stimulus is applied to the plate. A very soft tap, a very soft vibration to the plate. And one thing that you'll notice is that the fish in the top of the plate do not respond to that. However, those that are dosed with etomidate, this anesthetic, do respond to that soft tap. So we see very specific behavioral responses to a drug. Okay, so the behavior actually recapitulates the pharmacology here. So with colleagues at UCSF, David Coquel and Matt McCarroll, they have invented a technology platform that enables the monitoring behavior of zebrafish in these systems with a camera, and then you can apply a variety of stimuli. And you can look for the responses of zebrafish to neuroactive drugs. So what I've shown you with etomidate, that's a very peculiar response, very specific to anesthetics. So we can do small molecule screening. We can screen diverse libraries of compounds, looking for those that induce the same effect as etomidate. And we've actually done that with about 12,000 compounds in just a proof of principle experiment. And from that screen of 12,000 diverse compounds, what we have found are 4 unique chemical scaffolds that are able to exhibit this etomidate-like anesthetic effect in zebrafish. Now, working with Alan Basbaum in the anatomy department at UCSF, we've shown that one of the hits from that small molecule screen is actually able to anesthetize a mouse reversibly. So we can intravenously present this compound or administer this compound, and what you find is that the mouse is anesthetized, and within a couple of hours, the mouse wakes back up. Now, what's important about that proof of principle experiment is we've shown that we can discover anesthetics using this particular strategy. And etomidate was a good test case because etomidate is a drug that is known to have problematic side effects due to its chemical structure. So the structure that we have I've determined or discovered in our small molecule screen is very different from that of etomidate. So we don't think that we'll see that particular side effect, and we think that we'll have something that will be useful in medicine. So going forward, what we're hoping to do is apply this to a wide variety of areas in neuropharmacology with hopes of really transforming and accelerating drug discovery. Thank you.
Thank you to our wonderful discovery speakers and to all of you for joining us today. I look forward to the next time we can engage virtually and hopefully soon in person. Enjoy the rest of the Alumni Weekend programming.